Maybe you can start right away.
Okay. Should I start or just wait for?
No, start.
Okay. Yeah, so the topic of today's presentation is visualization of algebraic curves as it is. So first I would like to start with a brief review of Riemann surfaces. So Riemann surfaces grew out of the problem of thinking about multivalued functions just as a global holomorphic function defined on some domain. And Riemann introduced these Riemann surfaces to make those multivalued functions just global analytic functions, right? Like the logarithm function or like the square root function. So, but in modern times, we like to think about Riemann surfaces as complex manifolds of dimension 1. So, some examples are like these complex torus of C modulo some lattice of this form Z plus tau Z, where tau is in the upper half plane. So, and in fact, it can be proved that every elliptic curve is actually isomorphic to some complex torus of this form. And in fact, every compact Riemann surface is actually an algebraic curve. So compact Riemann surfaces being an analytic object, it is also important in from arithmetic perspective because compact Riemann surfaces are nothing but just algebraic curves. And here we will consider pairs of a Riemann surface and a map F from that Riemann surface to the projective complex projective plane. Sorry, so this should be math
Complex projective plane or line?
sorry, line. Yeah, so this should be C.
What is this? Lorentz space?
Yeah. So yes, I am defining that my pen is not working. Just a minute. Yes, something. I don't know, why my pen is not working. Just a minute. Yeah, now it's working. Yeah, so this should be math BPC. That means yeah. So this is also the Riemann sphere and or the complex projective line. And based on the type of identification between these pairs, we have two notions of Hurwitz spaces. So here is the notion. So we know that the set of all equivalence classes of Riemann surfaces of genus G is the moduli space MG. So this is a very standard object of study in modern times. And for these pairs, we have a notion of isomorphism. There are two notions of isomorphisms between these pairs. So one is that there is a map from x1 to x2 that is an isomorphism of Riemann surfaces such that this following diagram commutes. Okay, so this is the first notion, and the second notion is this is between two pairs x1 f1 and x2 f2, where f1 and f2 are maps from xi to p1c. So this notion is that there is an isomorphism between these two Riemann surfaces, such that this diagram commutes where mu is an Mobius transformation or a fractional linear transformation. That means it's of this form. Cz plus D, where A, B, C, D is inside SL to Z. SL to C. Yeah. Yeah. So is this definition clear?
Yes.
Okay. So based on these two definitions, we have two notions of Hurwitz spaces. Let's say the small Hurwitz space. So sometimes denoted by this symbol, which is defined to be the isomorphism classes of pairs in the first sense. That means in the sense of this figure, and where X has genus G and the map has degree D. And the big Hurwitz space denoted by this symbol, big HUR sub G comma D, which is defined to be the set of all isomorphism classes of pairs such that which is in the sense of this figure, such that genus of X is G and degree of F is equals to D. And it's easy to see that we can write this diagram in this form, right? P1C from these two, where this is the identity map, right?
Yes.
Yeah, and this since the identity map is itself Mobius transformation, we have this small Hurwitz space is actually contained inside the big Hurwitz space. And now we come to the part visualization. So here visualization does not mean that we are drawing the curve like we draw the graph of functions, etc. So we are trying to use the designs to capture the geometric information of a compact Riemann surface, and it will be clear as we continue that how these designs and some of their variants store the information of several Bailey functions, etc., and the geometric information of the compact Riemann surface. And that's what it means to visualize algebraic curves, because compact Riemann surfaces are algebraic curves, and using designs and Bailey functions, we are capturing the geometric information of a compact Riemann surface, and hence we are in some sense visualizing the algebraic curve. So first I will formally define design. So a design is a pair X comma D, where X is a compact Riemann surface and D is a connected finite graph. By finite graph, I mean that there are only finitely many vertices and finitely many edges between them. And it satisfies two properties, that each vertex is colored either black or white, and the adjacent vertices have different colors. And if I subtract the points and the edges of that graph from the Riemann surface, it will be divided into some topological, some geometric objects which are homeomorphic to the unit sphere in the complex plane. And that's why it is called the topological disks. And they are called the faces of those triangles, or maybe the, yeah. So they are called the faces. So genus of such a pair is nothing but the genus of X. And two designs are called equivalent if there exists an orientation preserving homeomorphism between these two Riemann surfaces X1 and X2, such that when I restrict that homomorphism to that graph, that becomes a homomorphism of between two graphs, D1 and D2. Yeah, so is this definition okay?
Yes, yes.
Yeah, so this is homomorphism in the sense of two graphs. So there is a notion of homomorphism between two graphs. So if I restrict phi to this graph, it becomes a homomorphism between these two graphs, D1 and D2. Yes, and here are two examples. So as you can see that this is a design over the Riemann sphere. And as I told that the vertices are colored either black or white, and the adjacent vertices are colored differently. And this is another design over the complex torus. But as you can see that the graph, actually the underlying graph is actually the same. But they are on two different Riemann surfaces of different genus. So is this clear, the figures?
Yes.
Yeah. So let me recall some notations. I have also used the same notations in my previous slide. In my previous representation, that is for a holomorphic map, if from a compact Riemann surface X to the projective complex projective line or the Riemann sphere, we denote by C of f to be the critical values of f. So the critical values of f are the points inside P1C, such that the cardinality of this pre-image is less than degree of f, or in some or the same is for some point q inside f inverse p, f is ramified at q. So there'll be some point q inside f inverse p such that f is ramified at q. Now, if necessary, we can compose f with a Mobius transformation, as we have seen before, and we can assume that if there are only 3 points which are critical values of f, then we can make those 3 values inside the set 0, 1, infinity, and we call such a map Bailey map if there are at most 3 critical values. And it is a deep theorem that those designs over compact Riemann surfaces and these Bailey maps are actually, there is a bijection between these the two classes of things, modulo some equivalences.
So this design can be drawn on which Riemann sphere, which Riemann surface?
Yeah, so this can be drawn on the so you can just compute the Euler point characteristic. For example, you can see that this will give rise to a triangulation with 2 faces. So this is one face, and the face outside it, and it has 1, 2, 3, 4 edges. So V minus C plus F, and there are 4 vertices. So 4 minus 4 plus 2 this is equals to 2. And we know that the Euler Poincare characteristic is equal to 2 minus 2g for a compact Riemann surface. So it is equals to 2 means that g equals to 0. So it actually then it is compatible with the genus of the Riemann sphere. So this can be drawn on the Riemann sphere. So we can check in this way by computing the Euler Poincare characteristic of this diagram. So
And you say this is corresponding to this rational
Yeah.
function.
yeah.
So you are considering this is as an algebraic curve or what?
Yeah. So this is an algebraic curve actually.
So you mean y equals this fraction? Algebraic curve.
Yeah, so you can consider this as a map from P1C to P1C.
Yes. Hmm.
And I am saying that this design correspond to this function, and this function is a Belly function.
So usually algebraic curve has two variables, x and y.
Yeah.
So this is the curve y equals this fraction.
Yeah.
Okay.
Yeah. You can consider this y equals to fx. Yeah. So, but this correspondence is not clear because it is a deep theorem, and there are several steps that how we go from a Belly function to a design, and from a design to a Belly function. But I have just here presented one example. So maybe, and there is no time left. So maybe we could have done it in detail. And there are another set of examples that trees are the simplest examples of designs. So like this. So by tree we mean a graph. So like this. So by tree we mean a graph with no cycles. So any tree on n vertices has n minus 1 edges, and any tree any such tree will give rise to a triangulation of a compact Riemann surface with only one face. Because it does not have any cycle, so it is actually not enclosing any extra surface or extra face. So it has only one face just outside this thing. And that's why, as we have done similarly, we can check that it is compatible with the genus of the Riemann sphere, and hence any such tree can be drawn on the Riemann sphere. And by that correspondence, it can be proved that the Belly functions that correspond to such trees are actually polynomials, and they have two critical values, and that's why they are Belly functions. So such polynomials are called Sabbath polynomials. So this is one example. This is the Belly. This is the design corresponding to this function. The polynomial x to the d. X to the 6.
Which one? Oh, I see. I see.
Yeah. So this is ramified at 0 because it has only one pre-image of 0, but its degree is 6. This is a degree 6 map.
So I suppose you can write down all Shabbat polynomials.
Yeah, I think so. But I am not sure if I can do that for any tree. Maybe there is an algorithm for writing all the Shabbat polynomial corresponding to any tree.
Or for any such graph.
Yeah. So the definition is that the Belly function corresponding to any such tree is a Sabbath polynomial.
Mhm.
And here are two simplest examples. And in fact, these are called the Chebyshev polynomials.
Ah, I see.
Yeah, so all the Chebyshev polynomials are Sabbath polynomials of these types of graphs.
I see.
So for example, this simple tree with two vertices is the first Chebyshev polynomial. The second, the three vertices tree is this second Chebyshev polynomial, and like that. So if I take the
Chebyshev polynomial is
yeah Chebyshev polynomial, this is the Chebyshev polynomial of first kind, and this satisfies this condition that Tn cos theta is equals to cos of n theta for all theta inside R. By induction, you can define from T1x all these Tnx, and they satisfy some recurrence.
so it's just the expression of cosine n theta in terms of cos theta and its powers.
Yeah. So you can just break this cos n theta by repeatedly by induction and see what is the form of this polynomial. And so in particular, this is that if I just take the line linear tree with n vertices, n plus 1 vertices, say, then it will correspond to the nth
I see.
Chebyshev polynomial, and does any Chebyshev polynomial is a Sabbath polynomial. Yeah. And we can now make layers of these Hurwitz spaces in terms of the ramification. This is something which is called the stratification of the Hurwitz spaces. So for any point inside the Riemann sphere, we call a point a critical value of a holomorphic function f from x to p1c if the inverse image has fewer points than the degree of it.
You just defined this, right?
Yeah. Sorry. Yeah. And yeah, so I'm just recalling things. And this is equivalent to saying that at least one point inside the preimage is preimage is there such that f is ramified at that point.
So in Bailey theory, we only concerned about R equal to 3, right?
We are only considering such that there are 3 ramification points.
3 critical values.
Yeah, 3 critical values. Yeah. And this is the layers of Hurwitz spaces denoted by the small HUR GDR, which are the set of equivalence classes in the sense we have defined earlier, such that the number of critical value is equal to R, and similarly define the larger Hurwitz space of level R or layer R. And if I consider a function f such that if I consider a function f from x to p1c such that all its R critical values satisfies that f inverse of p is just 1 less than the degree of p. So such functions are called generic functions. Okay. So the condition of for being a critical value is that we have to we should have that the preimage, the cardinality of the preimage of such a point is less than degree of f, and we are considering the simplest such case, or the optimal case, that is the cardinality is just 1 less than the degree. So for such a function, it can be deduced from the Riemann-Roch theorem that if df is the differential of that map, then the degree of the differential is equal to 2g minus 2, which is also equals to r minus 2d, where d is the degree of the map f and r is the number of critical values of f. And from that we can deduce that r is equal to 2 plus g plus 2 times g plus d minus 1. So this is the optimal case, and this shows that for any such map inside, so for any such pair xf, where x has genus G and f has degree D, the number of critical values can be at most 2 times G plus D minus 1.
I have one doubt. What is the difference between capital and lowered Hurwitz?
Sorry?
What is the difference between the definition of capital Hurwitz and lower Hurwitz?
Oh, the difference between it is defined earlier. Yeah. So here I am considering some larger aspect actually. So here we are taking all we are considering the isomorphisms of Riemann surfaces such that this diagram is commutative, where we have a Mobius transformation between these two maps, between these two copies of the projective line, right? And for the smaller Hurwitz space, we are not considering any Mobius transformation, but we are considering that these diagrams should be commutative. So this, in this sense, there are more equivalence classes, right?
Yes.
Yeah. So, yeah. Yeah. And then we can write these Hurwitz spaces in this disjoint union. So we are starting from r equals to 3 to, so this is in some sense a definition, a proper definition of the Hurwitz space. We are not considering the cases where the number of critical values is 1 or 2, because that seems to be not that complicated like these cases. So we actually define these Hurwitz spaces by this thing. We are only considering the ramification, or the critical values should be greater than equal to 3, and up to this bound we just have seen. So this thing is known as the stratification of Hurwitz spaces. But we will only consider the smallest possible or the simplest non-trivial case of ramification, where we will consider only those maps or those equivalence classes of Riemann surfaces and maps such that the number of critical values is 3. And we know that such maps are also called the Bailey maps. And it is another deep theorem that the Riemann surfaces X, or the equivalence classes of Riemann surfaces X, which admit a function from x1 to p1c such that the number of critical values of f is less than equal to 3. So this subset of this moduli space, that is the set of all equivalence classes of Riemann surfaces of genus G. So this particular subset actually is dense inside this MG. So topologically, it is enough to consider this subset. So it is enough to consider only such maps where the number of critical values is less than equal to 3, because it is dense inside this MG. inside this modular space. And this is another topological significance of studying the Bailey maps. Yeah, so is this clear?
Yes, yes.
Okay. And now we define the Bailey pairs and the main theme of the visualization theme. So a Bailey pair is a pair x comma beta, where x is a compact Riemann surface and beta is a Bailey map. That is a holomorphic map from that relates to the Riemann sphere, which has no more than 3 critical values. And first we will color the Riemann sphere in this following way. So I will first color the upper half plane in black, and then I will color the lower half plane in white, and then I will just consider the copy of the real projective line on this Riemann surface, which is the equator of this sphere actually, right? Yeah. And I will consider the 3 points on this 0, 1 and infinity, and I will color the part which is less than 0 of this thing in blue, and I will color the segment 0, 1 in green, and I will color the segment which is greater than 1 in red, and I will color the points 0, 1, infinity according to the color of the opposite sides of this triangle with vertices 0, 1, infinity. So the Riemann sphere colored in this way is called the Bailey sphere, and I have just tried to draw this thing inside this. So this is the copy of the real projective line inside the Riemann surface, and this is the coloring scheme.
Riemann sphere.
Yeah, sorry. Riemann sphere. Yeah, so this is the equator of the Riemann sphere, the colored Riemann sphere. And this is the copy of the real projective line. And real projective line, and this is the point at infinity I'm considering, and this is the 0, and this is 1. So I'm coloring all the points which are less than 0 and between infinity by blue. And I'm coloring all the points greater than 1 in red, and coloring all the points in between 0, 1 in green. And this is like a triangle. So the opposite, the 0 is opposite of this red segment, and hence I am coloring 0 in red. This 1 is opposite to this blue side, and hence I am coloring this in blue. And I'm coloring infinity, which is opposite to this segment, which is green, and hence I'm coloring this infinity in green. So is this clear, the Bailey sphere?
Yes, yes.
Okay. So more generally, we can define what is called the colored Desinde inference. So a colored Desinde inference is nothing but a triangulation of a compact Riemann surface with the following property, that every triangle, the triangular faces are either black or white, and the adjacent triangular faces have different colors. And the triangles have these following properties, that the every side and every vertices of the triangles are colored in blue, green, or red, and two incident objects have different colors. That means if we have two sides which are connected by an edge, then these two sides must have different colors. And if we have that two vertices are connected by an edge, then we must have that these two vertices have different color. So just we saw this. So this is a particular example of a Bailey of a colored Desinde inference.
Colored Desinde would be the just inverse image under Bailey map of this thing, right?
Yeah. So this is the, you can say that this is the simplest example of a colored Desinde inference. And we will use this simplest Disjoint on the Riemann sphere to construct a one-to-one correspondence between colored Disjoints and Bailey maps. So I'm just mentioning one direction of this correspondence. So if we are given a Bailey pair, that is a Riemann surface X and a Bailey map beta from X to P1C, then we have already colored the Riemann sphere, and we can consider the color of the point beta P inside P1C, right? And we will color the point P according to the color of beta P. That means if the color of beta P is black, then I will color P in black, and so on. So one can check that this coloring will make that will make a colored Disjoint over this compact Riemann surface X. And the converse is also true, but the converse actually needs some scheme theoretic details, that how we can go from our colored Disjoint to a Bailey pair. So, and that's how there is a one-to-one correspondence between the Bailey maps and the colored Disjoint. And hence we can combine this with the Bailey's theorem, which says that a compact Riemann surface is defined over algebraic number field, some algebraic number field, if and only if it admits a holomorphic map which has at most 3 critical values. So then we have this following theorem, that colored Disjoint actually correspond to this small Hurwitz space of Riemann surfaces defined over the algebraic numbers. So this is actually then rigorous form of what we are saying, that visualizing algebraic curves. Yeah, so this can be proved combining a theorem in a paper of Grothendieck, where he introduced the Disjoint and the theorem of Bailey. Yeah, so is this correspondence clear?
No, this last correspondence is not bit clear for which union.
Yeah, so this is we are considering only.
So previously you defined Hurwitz only over C, right?
Yeah, but you can just change the field of definition here.
Okay.
Yeah, so I am defining them on C, and I don't know a priori that if that map is defined over
Q bar.
U bar or not, but I am here forcing, or I am but here it is determined by the Bailey's theorem, that
Okay.
this is what this is the disjoint union of all pairs isomorphism classes of Riemann surfaces, and
Going from the C Hurwitz over C to Hurwitz over Q bar follows from Bailey's theorem, maybe, right?
Yeah, so that's why that's what I'm explaining. So yeah, so if this is nothing but the equivalence classes of pairs X and A, where genus of X is G, degree of F is D, and F has at most F has 3 critical values. So that means that the Riemann surface is defined over algebraic numbers by Bailey's theorem, right?
So this is some kind of scheme, right? So
Yeah.
So instead of Q bar, you could as well say complex numbers there, if you consider them as Riemann surfaces.
Yeah, but compact Riemann surfaces are also algebraic curves. So considering them as algebraic curves, I am sure by Bailey's theorem that they are defined over the algebraic numbers.
Yeah. So it is just so there is nothing special about Q bar here.
Yeah.
Because
So
there are
yeah.
because there are 3 branch points, you are saying
Yeah.
that they are automatically defined over Q bar.
Yeah.
Otherwise, you could as well say, if we did not know this Bayes' theorem,
Yeah.
it would
Yeah.
be
So then we could not have told if it were Q bar or C.
yeah, right, yeah.
Since we know Bayes' theorem, we can be sure that these curves are defined over algebraic numbers.
But do we understand something about the curves, underlying curves, their equations?
No, not. It's not
Because you
entirely clear
define
that.
this
Yeah.
Rubik
Yeah.
initially with the use of Riemann surface, not algebraic curves.
Yeah. Yeah. It's not a priori clear that if you give me a compact Riemann surface, and I will be able to give you the algebraic curve or the underlying the
So it is not
polynomial
quite
or-
correct to say that keep visualizing algebraic curves, perhaps.
Yeah, but it can be proved that every compact Riemann surface is an algebraic curve,
Theoretically,
Yeah.
it is.
and vice versa, that every algebraic curve is also a compact Riemann surface.
Yeah, that is.
No.
Yeah.
Now you see, when you use the word algebraic curve,
Yeah.
you mean non-singular only, or
Yeah. Of course.
yeah. So it is in terms of function fields, you are considering a non-singular model, but otherwise you can consider it something with singularities, and then yeah. Anyway,
Yeah.
Is this all, or you have more slides?
No. This is all, but I will include some references. I haven't got time to.
Okay.
Okay.
So this was the whole content of that paper of Sabbath?
No, there are some more specific examples and some more concepts which
Okay.
I have just omitted.
Okay, so is there any point in this discussion and proof of it that Chebyshev polynomial and Sabbath polynomial that goes into the proof of this?
No. That is just a specific case, but that is actually not in Sabbath's paper. I have taken it from a book called Introduction to Compact Riemann Surfaces and Disjoint Inference.
Okay, those Sabbath polynomials you taken from there, huh?
Yeah. So so I will cite that, and there are details. Yeah, so maybe.
So does he prove this theorem?
Yeah, sorry.
If he proves this theorem in that small paper?
No. There is no proof because it can be deduced from a combination of Bayes' theorem and what Grothendieck did in his paper, where he introduced this Desins and etc. So this is actually the rigorous form what we are saying about visualizing algebraic curves.
Is there any relation with the capital Hurwitz?
Sorry?
Capital Hurwitz that you define different space?
I'm not sure about that actually.
Okay.
now what was the question?
He defined two Hurwitz spaces now. I'm asking.
No, I think that's a minor point.
So some properties are kept invariant under Mobius transformations. So in those cases, we can consider the larger space, right? And if some properties are harmed by certain Mobius transformations, then we will only consider the identity and the smaller Hurwitz space. So based on the context, we will determine which space we will consider. Yeah.
I think it would be nice to write down the functions from P1 to P1. These are just rational functions.
Yeah.
With 3 critical points.
Yeah. That can be done, and that maybe some more examples are given in that book, Introduction to Riemann Surfaces and Desins Inference.
Who has written that book?
I have shared with you, Wolfert.
No, no,
Wolfert,
no, no,
I
no,
see.
no, 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 not Olfert. This is by Girondo and Gonzalez. Yeah, so
Okay.
I'm showing the book here.
Okay.
Okay, that is different book.
I think if you take the critical values to be 0, 1, infinity,
Yeah,
then you ask for rational functions which have these as critical values.
yeah,
Then it seems that it should be something like then if you have to specify the ramification.
yeah, yeah.
So it should be like x to the m, 1 minus x to the n,
Yeah.
divided by some.
Yeah, so those technical details are actually in this book and in. Yeah, so can you see my screen?
Yeah. Let us see your references.
He haven't put the references, he will put later, but he's showing the book. It is not visible, Shubhrajit, with your book.
Okay. Yeah, so maybe I have to. Yeah, switch the screen actually. I have to switch the screen.
Oh, you can see the book? Okay.
Yeah. So this is the book I'm referring to.
I see. Oh, Gonzalez DS. Oh, yeah, I see.
Yeah.
I see. Very good.
And there is another book by Jürgen Ulfert, and this is.
Yeah.
When was this book written?
2014, I think.
2014.
Just let confirm. Shubhrajit.
Yeah, I'm checking. So can you see this book?
Yeah.
Yeah, so this is another book. Designs the inference on compact Riemann or on Riemann surfaces by Jürgen Ulfert. So both these books have many things.
Very good.
So this book is published in 2012.
I think there should be a clear program from starting with just first enumerating all the rational functions.
Yeah.
Then enumerating elliptic functions. Something like that. I mean,
Yeah, so this computation of Bailey curves actually has been done by John Foyt in his recent papers. There are many works of him in his webpage. I have seen that that actually focuses on computations of such Bailey maps, etc.
I see.
Laila Snacks was in her talk perhaps not very much appreciated such things. It seems to me like that.
What?
Laila Snacks was not appreciating that thing, I think.
Oh, I see. Yeah, so
the Grothendieck plan was more of theoretical development.
Yeah.
Conceptual, not to go into. He mentioned that no computer program can be developed to compute in a uniform way.
No, but I think that both the computational and theoretical aspects are necessary, actually. Some specific computations show us the importance of doing these abstract things, right?
Yes.
Yeah. No, I certainly agree with you.
Yeah. Thanks. And some recent papers of John Foyt does many computations on modular forms, etc. Hilbert modular forms, L functions, etc.
But you need some programs for that, computer programs.
Yeah.
Have you used computer programs?
No. Yes, I am just learning Sage now.
Yeah.
That's the basic, very basic. There are many advanced such as Magma, Mathematica, etc. And sometimes they have used also supercomputers actually.
Yeah.
Yeah. For yeah. Yeah. So shall I stop sharing?
Yeah.
Yeah. So I have shared the slides with you, right?
No, yeah, you will say it means after putting the differential and everything,
Yeah. Yeah.
we will put there.
Yeah.
Okay, we will try to share your video also sometime
Okay.
on the YouTube. We have recorded it.
Okay.
Okay, then thanks.
Okay. Thank you.
See you in next trimester perhaps.
Okay.
Yeah. Very good lectures. Yeah.
Thank you. Thank you, sir.